So, okay. So good morning slash night, like evening, everyone, I guess. So yeah, thank you for attending this talk. Today I'll be talking about, and I would like to thank Karthik for giving this opportunity to present my uh, my work, with my joint work with one of my PhD students, one of my co-PhD students, Alejandro from University of Virginia. The topic of the talk today is inversion formulas for the modular J function. So what is modular J function? Well, this actually came up in the last talk that I had, but yeah, this is going to be a totally different direction that we are going to go into. Okay. So the modular J function is of very great importance, not only to number theory, but a lot of other fields. But today we will be just focusing on number theory. To name a few, one, and I talked about this last time as well, J function actually parameterizes the isomorphism classes of elliptic curves over C, which simply means that it actually gives you so basically what happens is that every elliptic curve can be thought of as a C mod some lattice, and you can evaluate J at that lattice. And it turns out that if two elliptic curves or two lattices have same J value, then those two elliptic curves are isomorphic. So that sort of gives you, and everything is over C. For other other fields of different characteristic, it's not true. There is a more general theory going on there. Second one, it generates the abelian extensions of imaginary quadratic extension. This is the main goal of our, this was the main goal of our talk last time. Well, for second part, probably I'll give it sometime in future when I'll have my laptop. But yeah, so it essentially says that if you have an imaginary quadratic extension, the J function evaluated at very special points actually gives you what's called the Hilbert class field. It's the maximal abelian unramified extension of a number field. So in the case of imaginary quadratic extension, you actually get that when you attach J value at very special points. And third, which is recent, which is the most famous result from, inspired by J function, the most important result that has come in the modern number theory is its deep connections with the monster-moonshine conjecture. So what is moonshine conjecture? It gives you, actually, it gives you, let me actually have it written down. It gives you an unexpected connection between the so-called monster group, which is this, what's the word? Which is the largest sporadic group. Okay, let me actually tell you some facts. So one of the biggest questions of 21st century were the classification of finite simple groups. And it has been classified completely. It turns out that every such group belongs to one of the 18 countably infinite families, like alternating groups, like cyclic groups of prime order, and so on. And there are 26 other groups which are called like sporadic groups, and monster group is the largest of them all. And actually what monster moonshine conjecture gives you, it gives you an unexpected connection between the monster group and the J function. And it is due to an observation of Conway and Norton that the coefficients, when you write J function as a Fourier expansion, its coefficient encode the graded dimension of the infinite dimensional graded algebra of monster group. It simply means that corresponding to monster groups, there exists a naturally occurring infinite dimensional graded algebra, and at each level, it's like a graded algebra, which means for each rank, you can say, or grade, there is a module and you add them together, and each module has some dimension that is given by the particular coefficients of this J function when you write it as a Fourier expansion. And this observation was proved not long ago. I'm guessing like it's like 20 years ago or so, by Richard Borchardt, which actually won him Fields Medal. So yeah. Not any question, but yeah. So these are the couple of remarks and why modular function is important. So what is modular J function? It actually is a bijection. It gives you a bijection between Riemann sphere and extended complex plane. I'll make this more precise. Obviously, there are natural ways to do this, but that has a very special type of bijection. What I want to like, what I want to raise, the question that I want to raise here is the following. Since this is a bijection between, this is a bijection, we are interested in the inverse formulas for the J function, right? And we are so the answer of this question is far from being proven. So we don't have any exact formula for the exact closed formula for the inverse of the J function. We have Fourier expansion for J, but for inverse, we don't know anything about that. This is essentially the same question as that we don't know, like we don't have any closed formula for elliptic integrals. So it's along the similar line. So obviously we are interested in finding these inverse formulas, right? And today we are going to talk about that. But keep in mind that the theorems that we prove actually give you a way to actually approximate the inverses. So still we don't have any closed formulas for this. So before we get started, let me give you an overview. So I'll start with some motivation, which I already did a bit before, but I'll define J function and everything. And then we'll talk about the recent developments towards this, like finding the inverse formulas for J function. And then I'll present my work, for which I need to include, I need to define hypersymmetric functions and all. Then I'll talk about some examples. Finally, I'll try to sketch a proof for you. And then I'll give you a connection of our work with Ramanujan's approximations of pi. Okay, so the modular J function is the function with this type of Fourier expansion, and this function is a modular function, which simply means modular function. So it's a function from upper half plane to complex plane, and it's modular over SL2Z. It simply means that it's invariant under the action of the SL2Z. So you take any matrix A, B, C, D in SL2Z, you act on the input variable, and you get the same function, like J of tau is equal to J of A tau plus B. So these are like the fractional linear transformations. And it satisfies the following two properties. First one, it is a meromorphic function with only one pole at infinity. And so the thing is, like J is so when we're talking about modular functions and we are talking about infinity, we are actually considering the infinity, which is like I infinity. So as y approaches towards infinity. And second, it has a constant term equal to 744. So if you have these two conditions, this is actually a unique such function. And 744 is just for historical reasons. As you can see, if you add any constant, like in this function, you will still get a modular function, because that will also satisfy this condition, right? So the 744 is there for just like, that's how it has been used in past. So yeah. So some special values of J function: J at I is equal to 1728. J at rho, where rho is the sixth root of unity, it's actually equal to 0. This is well known. This is actually coming from something that I defined last time, but I won't go into too much from details. I'm talking about these 2 points because, well, they are really significant in my talk later. Any questions before I go ahead? Okay. So since J function is a function on upper half plane, and it is invariant under SL2Z, we can actually look at the action of SL2Z on H, right? and we can get something like, we can mod out like do SL2Z mod like H, and we look at the equivalence classes, which means that all the points for which where they are SL2Z invariant, and we club them together, right? And it turns out the fundamental domain for this looks something like this. Like, so you might have seen this picture many times if you ever attended any of the like modular forms or elliptic curve talks or something. So this is a fundamental domain for SL2Z, like H mod SL2Z. So this is the correspondence that I was talking about, like the normal. So you can think of this also as like Riemann sphere, and the J function gives you a bijection from this to the complex plane, extended complex plane. And we are interested in finding its inverse map, right? So let's talk about some recent development. When I'm saying recent, it's like 2021. So in 2021, Calderaro, Hay, and Huang conjectured something, a very unexpected behavior, because their conjecture comes from mirror symmetries, and its proof is actually coming from the theory of like number theory. So what is the conjecture? Let tau belongs to SL2Z/H. So you can think of just that tau belongs to this this fundamental domain, which has non-trivial stabilizers. And it turns out when you're talking about non-trivial stabilizers, there are just 3 points, I, rho, and infinity. And I have excluded that infinity here for some reasons, because well, that's not included in their conjecture, and it has been sort of like solved in that case before. So consider the Taylor series of this J function around that tau. So I talked about this. So you can think of this J, this Fourier expansion as the expansion of J around infinity, right? That's one way to think about it. But what we can do is we can actually look at its Taylor expansion around other points, and their conjecture actually talks about that. Says that consider the Taylor expansion of J function around these 2 points. Then there exist very special functions. Let's call them omega of tau. I'll make this more precise in a bit. But they say, okay, there are some special functions. When you put them there, actually, the Taylor series expansion for them turns out to be a rational function in T. So what you're doing, so in general, a priori, we don't like, you should not expect this, because if you look at the Taylor expansion of J function, it's really like a not connected, or like it has an infinite expansion with no no pattern or any obvious way that they should turn out to be a rational function. But what they conjecture is that there are some special functions. They call them, well, we call here omega of t. When you input them, it turns out to be a rational function. So you can think of these as the inverse formulas, right? Since what the right hand side is a rational function in t, you can solve this. So if you want to say, for example, you want to solve t or j of tau is equal to some alpha, you solve this rational function equal to alpha, and then you get values for t, right? And then when you input it here, you get the exact value of tau, which gives you that value, right? So you can think of them as the inversion formulas. To make these more precise, let me define some notation / definitions. So for any tau star belonging to I and rho, we have these uniformizing maps. So S tau is from S to D, and S tau inverse is actually from D to H. And these are well known. So these are like the not the standard uniformizing map, but we have actually normalized it with some like with this factor 2 pi omega t star omega tau star, where omega tau star is the so-called Chawla-Selberg period. So this is simply some ratio of gamma functions. Well, I'm being a bit mysterious here. Actually, these turn out to be, these come naturally when you are studying the theory of modular forms. And these are the so-called so when you have a modular form, you evaluate it, for example, at I, then you get some transcendental part and some algebraic part. And the transcendental part is this in each of these cases. You take any modular form, and when you evaluate at I, you get something like this. And similarly, rho here. But for time being, just assume them to be some ratios of some gamma functions evaluated at certain points. Well, I don't want to go into much detail, but this is like somehow kind of like, okay, never mind. Yeah. There's a whole beautiful theory behind that. Okay, so how do you get a Taylor expansion of J function around tau star? As I told you before, it has a Fourier expansion, but we don't have any closed formula even for J function itself. We know the properties, that there is a function which satisfies these properties. So we can talk about, like, we can look at or find its Fourier expansion and everything else. But in general, finding there is no closed formula for J function. So in general, finding the Taylor expansion of J function around any point is very difficult. And you can get them from the theory of Taylor expansion of any modular form. That's like a standard thing. You can find it in any modular form book. It simply is there's J evaluated as tau inverse of W. So you're sort of shifting the centers from, well, you're shifting the center from that point to 0. So this is sort of like, if you go back here, you will see that when you put this is equal to 0, you actually get the tau star here. So it's like at this point, we are just considering this W belongs to this. So this is how it's defined. J of S tau inverse of W is this summation, where this 4 pi times, this is the imaginary part of tau, the whole thing to the power n, and then there is this nth derivative of J function. Now, this is what I was talking about, that this part, evaluating this part is pretty hard in general. But actually, when tau star is equal to I and rho, it has been well studied and we know what this is. Okay. So in these cases, the Taylor expansion, I mean, it has a closed formula in this case when you evaluate at these points, but I won't be writing it here. Well, when we don't need that. And it turns out that it's Taylor expansion looks something like this. And this actually verifies the fact that I talked about earlier, right? If you remember, where was it? Yeah, we looked at special values, right? J of I is equal to 1728. So the first value, the 0th derivative, should be 1728. And for rho, it should be 0. And that's what you can see here. 1728, and then you can see there is no constant factor here. Okay, so what is this conjecture that they gave? For that, we need this notation. So this is called the, I guess, the M, well, I don't know the actually exact word for this. So it simply is the following: m n minus r. You have three positive integers, m, n, and r, and assume that r is less than m, so that this doesn't become negative or anything. M, n minus r, and then there are like four, like m, capital M factorial symbols here. This is simply like you are looking at, instead of, so this is like a factorial, but actually you are not looking at the consecutive terms. You are actually looking for consecutive terms in an arithmetic progression, right? So, and you product them together, you get something like this. In that case, with these notations, they define these two special functions. So hi of t is summation is equal to 0 to infinity minus 1 to the power n, 4n minus 1, and then 4 factorial. This simply means that you're looking at like 4 minus 1, then 4 times 2 minus 1, 4 times 3 minus 1, up to 4 times n minus 1 minus 1. And this whole square divided by this factorial, and this is a standard factorial. Okay. No, sorry, there's a misprint. There should be 2 factorials here. T to the power 2n plus 1, and similarly here there should be 2 factorials. And so this is for I, and these are going to give you the special functions that I was talking about. So h rho is defined in the following way. Again, in the denominator there should be like 3 factorials. My bad, I noticed that. If you have these 2 functions, then their conjecture is the following. The following are true. J, when evaluated at Si inverse of the ratios of those 2 functions, so you can see that this divided by this is a really complex function, right? It has a like a really random Fourier expansion, random expansion in general. And it turns out when you input that here, miraculously, the right hand side turns out to be this nice looking rational function in T, right? And similarly for rho or around rho, you have this J when evaluated at S rho inverse of point plus 1 divided by 3. This is this nice function. Okay. You can think of them as a generalization of the fact that j of I is equal to 1728 and j of rho is equal to 0 respectively, in the sense that when you put these values, for example, you can, when you put t is equal to 0 in the right hand side, you will see that the first term becomes 1728 and the second one becomes 0 because of this factor, right? So what I'm saying here is that the way at t is equal to 0, this side, these two will actually be SL2Z equivalent to I and rho respectively. So in some sense, you can think of them as like the like you have this disk. So I have not specified here, but actually this, you want this t to be in a certain disk. When that is the case, you can think of them as you have this map from a disk to like complex plane, where at the center it's taking the value I. Okay. Then recently in 2022, Hong, Mertens, like January 2022, I guess, Hong, Mertens, Onu, and Zhang, and Kanono proved the conjecture. They proved that the conjecture is true. And the proof uses the theory of hypergeometric functions, specifically the hypergeometric functions of signature 2 and 3. I have thrown out these words. I'll define it in a bit. But there are well studied. So hypergeometric functions are well studied objects, and in that, like even in that, the signature 2, 3 are like really well known, well studied. And with these two, there are two more signatures 4 and 6 are also here. So Canono and his co-authors actually raised this question in their paper, that are there other such similar relations that are coming from signature 4 and 6, right? And our work is to show that indeed this is true, and to define that to I guess, what is the word? Anyway, yeah, to give our results, I guess we need to define hypergeometric functions, obviously, and define what these things are, right? So it's a very famous object in, like, hypergeometric functions are pretty famous anyway, but Gauss hypergeometric functions are the first instances where this was seen. This simply for a parameter a, b, and c belonging to real numbers, as you don't want c to be a negative integer, because you can see that c is here in the denominator. So I mean, it goes to infinity or something like that. But yeah, the 2f1 Gaussian hypergeometric functions written by this are defined the following way: 2f1 a, b, c, and z. So these are the parameters, and this is the variable, is equal to summation n is equal to 0 to infinity. This is again that symbol, if you remember. Well, yeah, I did not define this symbol, right? Okay, so this is like the okay. Let me see if I can write. Go back, see if I can just write it. I mean, hopefully I can. Let's see. I'm trying to guess where it is. Okay, there it is. So this, let's see if I can write it here. Okay, it's weird. So for any a, define it as follows. Write it as a times a plus 1 times, and so on up to a plus n minus 1. Oh, okay, I did it. Okay, so this is how to define it. So this, you have, like, in the numerator you have a n, b n, and then in the denominator c n, z to the power n divided by n factorial. And you want your absolute value of z to be less than 1. So this function is defined in complex plane, because the thing is, like, this also has an integral representation, and using that you can actually extend this to whole complex plane, excluding one line. You want the space to be like, since like you're talking about like integrals, you want it to be like simply connected to make everything nice, right? So it has a complex analytic continuation to the whole complex plane except 1 to infinity. but this is the place where you can actually approximate it, and that is important. When absolute value of z is less than 1, actually you can easily approximate it by any like by mathematical or whatever. Well, the way we so on, if you want to keep this function continuous, then obviously you have to exclude 1 to infinity, but we can actually define this function on 1 to infinity as well, because the point is that it has 2 limits, right? You can either approach from top or from the bottom. And the way throughout this talk, I'll be like these function, I'll define it on these points, and I will be defining it by approaching from the top. So this is what the second point is. And third, which is how actually originally it was studied. So Gauss was interested in the solution of this differential equation. And it turns out that solution, when you solve it, like the standard procedure, like you write a full like power series expansion, standard power series expansion, you get a recurrence relation. And using that, when you solve it, you'll get this. Okay, any questions so far? Okay. Okay, so some examples here. So for example, if you look at, sorry, it's sub 2, 2f1 of 1 comma 1 comma 2 comma minus z, its actual summation is equal to 0 to infinity of 1n, 1n, 2n, and minus z to the power n divided by n factorial. What is 1n? It's product, right? 1, 2, 3, 4, and so on up to n, right? So it's exactly n factorial. And there's also n factorial. And this one, since we are starting at 2, it's n plus 1 factorial, right? So you get something like this. And now you cancel out certain terms. You're left with something like this. And you know what this is. This is pretty famous. I mean, there's log 1 plus z upon z, right? Okay. And another example is if you have, in general, if you have like a, b, and b, well, not in general, it's not the generalization of above, but yeah, if you have like a, b, and b, in that case, you can see it looks something like this, and these b and b factor cancel out, and you are left with just this. And this, when you solve this, actually you'll find that is equal to 1 minus z to the power minus 3. So there are these like, just to show the like these abstract formula doesn't look nice, but these terms sometimes actually convert to some nice function. Okay. So so what we prove is the following. So in our case, so in their case, special functions were actually ratios of 2 power series expansions, right? And you can think of like these things also as like our 2f1s as some sort of power series expansion in certain disk. Or actually, you can look at like talk about analytic continuation of that, but we'll be just focused on this. So you have this Fourier expansion, not Fourier, power series expansion. So in our case, the special functions are this: ci of t is t times 2f1 evaluated these parameters, and the variable is 40 squared divided by this like parameters 1 upon 4, 1 upon 4 half, and 40 squared, and 0 is equal to this 5 by 6, 5 by 6, 5 by 3, and 1 by 6, 1 by 6, 1 by 3. This. Then we prove that for absolute value of t less than half, j when evaluated at like SI inverse of ci of t plus 1 divided by 2, you get this nice formula for t. And when absolute value of t is less than 1 upon cube root of 3, cube root of 2, sorry, then j of SI inverse, S rho inverse of C rho of t is this nice formula, right? One good thing about our formulas is that actually you can see, for example, here, like each of these terms are in t square, right? And here, each of these terms are like in t cubed instead of t. So solving these is essentially solving degree 3 and degree 2 polynomial, right? So yeah, in this case, you can do everything by hand, I guess, at least in this case, in the second case, because like you are solving a quadratic. And then whatever solution you get, you will look at the cube root of that. Okay, so again, when you put t is equal to 0 on the right-hand side, you will see that you will get, so when you put t is equal to 0, from the numerator, you get minus 3 cubed, and from denominator, you have minus 1. So when you multiply them together, you get 1728 again. So, and when you put t is equal to 0 here, you can see that this becomes 0 again. Then again, you can think of these two as like the inversion formulas around I and rho respectively in that regard, right? Okay, so this is the first remark. The second remark is that actually our formulas are true for whole complex plane, but for computational purposes, we restrict our domain to just these values, because these are the values where we have these power series expansion formulas for hypersymmetric functions. So we can easily approximate these functions. But in general, all these formulas are going to be true for extended complex plane. Not well, not extended. Yeah, okay. And then the third point I already talked about, it's like j of tau is equal to alpha boils down to solving a quadratic or a cubic, right? Okay. So any questions so far? No? Okay. So yeah, so let's see this in action. How do we solve this? So I'll present two examples. First one is a very well-known, we'll confirm very well-known fact about the values of j function at very special points. So j, when evaluated at square root of -2, actually is equal to 8,000. And we'll verify that. Okay. So we want to solve, we are going to use the first formula, I guess. So let me just go back here. We are using this formula. So what we want to solve, we want to find a t such that when evaluated, when you put t here, you get right hand side becomes 8,000, right? So let's do that. We assume t square is equal to x, and we solve this cubic. And we find that the solution, one of these solutions, when you like find one solution and then do a square root, you get something like this. And you can easily approximate these, right? And one thing you notice is that the absolute value of the solution is less than half. Then what we do is we put these values okay, again here, and we use a computer to actually approximate it. And when we approximate it using 3,000 terms, first 3,000 terms, we get that CI of T naught is equal to this. So we are evaluating J at this point. So let's evaluate that. We get that this is equal to this. And one thing you notice, okay, you are expecting that this turns out to be square root of -2, but indeed it's not. But the point is that it is something which is SL2Z equivalent to this. And how do you check that? If you look at something like -1 upon T naught plus 1, there is a standard procedure. What you want to do is you want to send your square root of -2 in the fundamental domain as well as this point. And you can do that. When you do that, you get that this is the formula, how you approach in the fundamental domain, and you get this value, which is approximately equal to square root of -2. And when you do the computations, it turns out that this approximation is actually these like equal up to or correct up to 364 decimal places. Okay, so this sort of verifies that indeed this like j of square root of -2 is equal to 8,000. As I told you before, our formulas are far from being the closed formulas that we want. That will be the ideal goal. But we can just approximate these functions like the inverse for j. The second one, we'll try to find tau naught such that j of tau naught is equal to -50,000. So we solve this. We use the second formula. So we evaluate this is equal to -50,000, where x is equal to the cubed. And you solve this, and you will find that one of the solutions is equal to this. Again, notice that absolute value of T naught, whatever you get, is less than 1 upon cube root of 2, which is approximately equal to this. So we chose this value because it's really close to the disk, the part that we don't want to like go further ahead. And since we are very close, we need to use more than like 3,000 terms. In this case, we use 5,000 terms to get this value of 0 of T naught. And we evaluate as rho inverse of 0 of T naught, we get something like this. And it turns out when you put like in, so there are these standard packages where you can actually evaluate J function. So when you evaluate a tau naught, you get that it's actually equal to this. So it's sort of like verifies whatever answer you are getting is correct. And it's actually, the approximation is correct up to 16 decimal places. And this 16 is low because of the fact that actually our value is very close to the disk, right? So actually, to get really exact approximations, like really nice approximation, we need to use more than 5,000 terms. Okay. Okay, so let's look at the sketch of the proof. So recall our special function. I'll prove the first of the two parts. So we had this special function, right? T times 2f1 well at like the hypergeometric function at these points, or like these parameters divided by a hypergeometric functions at the parameter 1/4, 1/4, half, and 4t squared. And we say that if absolute value of t is less than half, then we have this formula. Okay, so at this point, I would like to tell you what the signature means. Signature simply means that hypergeometric function of signature R is the following: lambda sub R of z. This is the shorthand for this. Is 2f1 when you have like 1 upon R, R minus 1 upon R, 1 and z. So for example, when R is equal to say 4, it's going to be 1 upon 4, 4 minus 1, which is 3 upon 4, and then 1 and z. And these are going to be like important in our proof, because what we will do is we'll convert these. So a lot of things are known for these formulas. So what we'll do is we'll interpolate these functions and actually get a function which looks like this, or a linear combination which looks like this. And now the theory in this case is well known, and we'll use the formulas from there to prove our result. So in particular, as I said, lambda sub 4 of z is equal to 2f1 at 1 upon 4, 3 upon 4, 1 and z. Okay. So hypergeometric functions have really nice properties. They have singularities at 0, not in the sense of like the singularity as like the singularity of function. These are the special points of the differential equation. So these are 0, 1, and infinity. And there are formulas, for example, this one, that actually give you a way to interpolate between these values. So for example, you can think of this formula as follows. You can think of this as this z goes to infinity, you have so 2f1 when evaluated at z can be written as linear combination of some hypergeometric functions evaluated at 1 upon z and 1 minus 1 upon z, right? So for example, when z goes to infinity, this thing goes to 0 and this thing goes to 1. So you can think of this as a way to send the point infinity to the points 0 and 1, or a linear combination of those. And we are going to use this. So the proof of the theorem goes as follows. Assume that the argument of t is between 0 and pi/2. This is because there are squares and other factors there, and we want to like, what is the word? Well, yeah, okay. Right now I cannot come with the word. What is that? Yeah, branch cuts and all. So you want to avoid that. I'll explain how, when you change the argument, how this affects later. But for time being, let's assume that the argument of t is between 0 and pi/2. I'm talking about this because, you know, if you look at the formulas, there are t square, like there is t square here. That is going to affect later. So, and here we want to use these formulas with very specific values of a, b, and c, which are fractional values, and we have these factors, right? So because of that, we want to restrict it here. In that case, take a and b to be equal to 3/4 and c equal to 3/2 and z is equal to 4t square. So here, let's go back here and see. So a is equal to 3/4. That's what we did, right? Yeah. So 3/4, 3/4, and then 3/2. When you put it here, you will see the first term becomes what? 3/4 minus 3/2 plus 1, right? That becomes 3/4 minus 3/2. That becomes 1/4. And then you have 3/4, and this part becomes 1. And similarly here, if you check that this becomes 3/4, this becomes 1/4, and this becomes, the whole thing becomes 1. So what you get is the following. In the shorthand notation that we defined, you'll get that 2f1 at these parameters is equal to some ratios of gamma function times this factor. And this is why we are actually restricting our argument to be between 0 and pi/2. This factor comes out, and you are inside, you are left with lambda 4 of 1 upon 4t squared plus e to the power 3 pi I upon 4 times lambda 4 of 1 minus 1 upon 4t squared. Similarly, what you can do is, so this is the way you interpolated this function. There was one more function, which was 1 upon 4. And when you choose a is equal to b is equal to 1 upon 4 and c is equal to 1 upon 2, and z is equal to 4t squared, actually you get something like this. And one nice thing you can notice is that these factors are same, right? So what you do at this point, you divide this by this. And then when you divide this by this, you will get some ratios of gamma functions times this factor times the ratio of this part, right? And when you rearrange them, you'll get something like this. And what was CIA of t again? It was this function. This t is coming from those ratios of 1 upon 4t squared to the power half divided by, or 3 by 4 divided by 1 upon 4t squared to the power 1 by 4. You're coming this factor, getting this factor from there, and this factor is coming from the ratio, and then the ratios of gamma factor is actually giving you that Chowla-Selberg period that I talked about. So when you divide, you get something like this. So this is the Chowla-Selberg period, and this 2 pi comes from, obviously, when you are using, well, I guess that's the factor. Oh yeah, okay. So that is coming from the fact that omega I itself had like that 2 pi factor. Okay, and what you can do is you can actually bring out, so from numerator and denominator, you can pull out lambda 4 evaluated at 1 upon, evaluated at 1 minus 1 upon 4t square. When you do that, this actually turns out something like this, right? Lambda 4 of this divided by this, whole thing divided by this or something. And when you solve, you get something like this. And this actually looks nice, right? This actually looks like those uniformizing maps when you value like uniformizing map at I, right? So what you can do is you can take the inverse, SI inverse of CIT divided by 2 pi omega I squared. And in shorthand, I have written like a small SI inverse for that. It's actually 2 tau minus 1. So this implies that this tau, whatever we actually chose here, is equal to this factor, right? And as I told you before, that in this case, these sort of like inversion formulas have been well studied. So as I told you that I'll let you know what happens if you choose arbitrary arguments. What happens is that when, so all these like things go pretty nicely, but these factors, e to the power, the factors actually change if you change the argument. And how does that affect your calculation is the follows. If 0 to pi by 2, you have this formula for CIT divided by 2 pi omega I squared. If you have your argument between pi by 2 and pi, you get a factor which actually will give you something like this, where this tau is actually this factor. And when you have like minus pi by 2 to 0, you have this, and minus pi to minus pi to minus pi by 2. And you get this factor. And when you evaluate this factor at which you want to actually get the j value, you get these factors, tau minus 1 divided by 2 tau minus 1, this factor and this factor. And luckily, what we have is the following. Each of these are actually SL2Z equivalent. So when you have like these values are SL2Z equivalent, which means that j of any of these are going to be same. So what I'm trying to say is that the boundaries, they have the same values, so we can patch them together. And we can, when we are evaluating j at these points, they actually turn out to be a continuous function on the whole disk. That's pretty nice. So yeah, so we have these different, like the argument changed the definition of, or the factors that are coming in these ratios, but when you evaluate at j, they turn out to be same. So we don't have to care about that much. And then we have these formulas, as I told you before, that in the case of classical, like in the classical case, these formulas are well known. If tau is equal to this, then j evaluated at tau is going to give you this. So you can think of these as like the inversion formulas around infinity, because when you put gamma is equal to infinity, you get this part to become infinity, right? So this tau sort of represents the I infinity case. And when you apply this inversion theorem for gamma is equal to 1 minus 1 upon 4t square, this gives you this formula, which is like the inversion around I, right? Yeah, so this concludes the proof, the thing that we wanted. Any questions? Okay. So yeah, now the proof of the second part. You had this special function, and in this case, again, the similar argument follows. You have this formula again. We are going to use the classical inversion formulas for like signature 6 case. Again, we want to restrict our argument to this, and we want to choose certain values. We want to apply that preposition again. And in this case, you get something like this, where tau is the ratio of these two functions. But now instead of lambda 4, we have lambda 6. And when you change the argument, this is how it is affected. Again, this looks nice, but this was more complicated one because you don't have, like, in that case, you had four actually intervals. Here you have like 1, 2, 3, 4, 5, 6 intervals, and then it turns out that on the I guess rays or arrays which separate these intervals, it turns out there the definition was actually different. So calculating all these things was a bit more tricky. Anyway, in the end, you get that all these, when you do S row inverse of these things, you get something like this, and all of these are SL2Z equivalent. Okay, I didn't explain what I mean by SL2Z equivalent. It simply means that there exists a matrix in SL2Z that sends this point to this point, or this point to this point, or this point to this point. It interchanges. For example, when you want to go from this point to this point, the matrix that you want to consider is the following: 1, 1, 0, 1, right? That's called the translation matrix, and it sends tau to tau plus 1. And I don't want to think about this one, but yeah, it's something like that. It's a combination of like what's called translation and inversion matrices that span this SL2Z. Okay, and in this case, we use this well-known formula by, again, Bernd, Bhargava, and Graven. It's from, I think, 1990s, if I'm not mistaken, 95 or something like that. And they gave these inversion formulas, but this you can, again, as I told you, these can be thought of as the inversion around infinity. And when you put gamma is equal to 1 upon t, you get this formula. Okay, so we talked about this, but the thing is, like, how these theories originated. It turns out that the whole theory hinted towards, the whole theory was from Ramanujan himself. He gave these, you might have heard if you attended any like I don't know, any of the Ken's lectures, I guess, Ken's talks. He talks about Ramanujan a lot. Like, his whole inspiration is from Ramanujan. There's a nice story behind that. But anyway, so Ramanujan actually gave these crazy approximating formulas for pi. So you gave like these, like, so you have this infinite sum. You can actually like sum this in a computer up to a certain point, and that gives you a nice approximation for 1 upon pi, which in turn gives you a nice approximation for pi. And not only these two formulas, there were actually he gave a whole lot, at least 20 to 30 more formulas regarding this, right? So when he gave these formulas, like, it was like in 1910, 1915 or something like that, I don't remember exactly. But later, when the Ramanujan's lost notebooks were found, people thought of this, like, started thinking about these things, how he came up with these ideas. And since there are more than 20 formulas for approximating pi, they thought, is there any underlying theory behind that? It turns out, yes, there is. The formulas were proved, all the formulas were proved by Bro and brothers in 1987. And whatever theory they used the theory of hypersymmetric functions, but whatever they came up with was actually the tip of the iceberg. The whole theory later was developed by Bernd, Bhargava, and Graven in their 1995 paper, where they had this whole 80-page paper where they developed this whole theory. They call this the Ramanujan's theory of elliptic functions to alternate basis. So this elliptic function comes from the fact that all the hypergeometric functions, or all the Gauss hypergeometric functions, can be thought of as elliptic functions, or can be thought of as elliptic integrals, like integral of some functions which are elliptic. Okay, and this alternate basis, I'll tell what that means. This alternate basis actually comes from a brilliant idea from Ramanujan. So recall, if you have q is equal to e to the power 2 pi I tau, which means that you are looking at the Fourier expansion of j, then the j had this formula, right? 1 upon q plus 744 plus this factor plus whatever. And this 1 upon q is actually gives you that at infinity you have a pole. Sorry. The brilliant idea of Ramanujan is he said that, okay, so you can think of this as q as the basis, like the base of this expansion, right? So q series with q equal to this. He said, okay, what if we change the definition of q? How does that affect the whole, like the expansion of this J function? So one example, I mean, I gave you two theorems which had the same idea. So an example is the following: is if we replace this e to the power 2 pi I tau by this function, e to the power minus 2 pi times this ratios of hypersymmetric functions. It turns out that when you evaluate j at tau, this turns out to be a nice rational function in this input variable gamma. So what you did, you instead of looking at the Fourier expansion, you replace t, this tau, by a very nice family of, I guess, functions. Like you can think of this that you replace this tau by a very special family, which is coming from the ratios of hypersymmetric functions. So this is so-called signature 2 hypersymmetric functions, like half, half, one, and whatever argument you want to use. It turns out when you do that, you get this like crazy. Somehow this whole like expansion turn into this like rational function. I mean, rational function in the input variable, right? So again, you can, as I mentioned a lot of times, you can think of these inversion formulas as the inversion around infinity. And there are three special points when you look at this fundamental domain. Those 3 points are infinity, I, and rho, because those are the point where like there are a lot of properties that are actually nice about those 3 points. But one that I mentioned was that these 3 points are the only points which are which have non-trivial stabilizers under the action of SL2Z. So it was natural that there might be similar theories when you look at the, instead of Fourier expansion, you look at the Taylor expansion around these points, and that's what our results talk about. So just as a summary, we have these special functions, which when evaluated at, or when you look at the SI inverse of these, with Ci of t plus 1 divided by 2, this gives you this rational function. And similarly, in the case of I, you have this. Yeah, okay, I'll stop here. I think I did a lot of gibberish here, I guess. Any questions?